Hi, I'm Yael, and this talk is about network optimization algorithms in the congest model, which are also secure against eavesdropper adversaries. And this is a joint work with Merav and Eylon Yogev. The distributed model that we consider is a congest model, where the network is modeled as an undirected graph with n vertices, and initially every vertex only has a local view of the network, so each vertex only knows its incident edges. Then the computation proceeds in synchronous rounds, where we also have bandwidth limitations that in each round every vertex can send at most log n many bits on each one of the incident edges. And usually the main complexity measure that we look at is the round complexity, the number of rounds it takes us to solve some problem. And now let's assume that there is some evil adversary that is eavesdropping to some of the edges in my graph. So this eavesdropper can now see all the messages sent over these edges. Now, using this information, the adversary might deduce some private or sensitive information that I don't want it to learn. So the goal in this work was to design algorithms in the congest model that are on the one hand efficient in terms of number of rounds, but also on the other hand secure, which in the high level means that the adversary gains no information. And I will now define exactly what this means. So we consider a passive adversary called an eavesdropper that controls a fixed set of F adversarial edges and sees all the messages sent over them. And this adversary is computationally unbounded. It knows the graph topology and also the algorithm that we execute. However, it is oblivious to the input of the vertices and also to their internal randomness. And the security notion that we consider is information theoretic, and it means that the eavesdropper is required to learn nothing on the private input of the vertices. And to be more concrete, if we have some algorithm A, we say that it is F secure if for every set of at most F adversarial edges, the messages seen by the adversary and the input of the vertices are independent random variables. Now, in previous work, secure distributed algorithms have been mainly studied in complete graphs in the cryptographic community. As for general graphs, Jane gave an optimal algorithm using diameter many rounds for the secure unicast problem, where we have some specific source vertex that wants to send a message to a single target vertex. In a recent work, we also gave a secure algorithm for broadcast, where here we have some source vertex that wants to send the message to all the other vertices in the graph. As for general graph problems, it was implicitly shown in a previous work that we can actually take any non-secure distributed algorithm and compile it into an equivalent secure algorithm. Well, this compiler works in a round-by-round manner, and this results in multiplicative round overhead of d to the power of f. So even for logarithmic many adversarial edges, the round overhead is at least linear in the number of vertices. And what we did in this work is we looked at secure algorithms for the class of global optimization problems, which has been highly studied in the congest model. And one of the main optimization problems that we looked at is the minimum spanning tree, where the input is a weight function defined on the graph edges. So the input of every vertex is defined to be the weights of its incident edges. And the goal is to output a spanning tree of total minimum weight, where in the distributed output format, we require that every vertex is going to know which one of its incident edges are included in the output spanning tree. So in order to obtain security for this problem, it is required that the adversary gains no information on the weights of the edges. So for this problem, we gave an F-secure randomized algorithm for graphs that are order F edge connected, with round complexity that is approximately d plus f square root n many rounds. And this O tilde hides polylogarithmic factors in n. So, and the security notion that we gain here is statistical security, meaning that the algorithm is secure with high probability. So at least for polylogarithmic many adversarial edges, we get round complexity that nearly matches the non-secure round complexity for this problem. And this algorithm can also be extended to solve other optimization problems, such as approximate minimum cut and partwise aggregation, where partwise aggregation can actually be used to solve many other classical optimization problems. Okay, and one of the main tools that we use in our algorithms is a general compiler that takes any distributed non-secure algorithm and converts it into an equivalent secure algorithm, where also our round overhead depends on a parameter called edge congestion. And the edge congestion of an algorithm is the maximum number of messages sent over an edge throughout the entire execution of the algorithm. So what did we show? We showed that if I have a graph which is order F connected, I can take any around algorithm with congestion C and convert it into an equivalent F secure algorithm with additive round overhead of approximately D plus F square root Cn plus Cf many rounds. So intuitively, if the algorithm has low edge congestion, we get an additive round overhead of approximately F square root n. And this is in contrast to the previous known compiler, which had multiplicative round overhead of d to the power of f. Okay, so I'll now give the high-level ideas of the congestion-sensitive compiler, and then turn to talk about the secure minimum spanning tree algorithm. Okay, so in our compiler, we're given an R-round algorithm A with congestion C, and the goal is to construct an equivalent algorithm that is also F-secure, meaning that it is secure against F adversarial edges. So the main idea of our compiler that we are going to broadcast sufficient many random keys that are unknown to the adversary. This we can do using the secure broadcast algorithm. And then in each round, when V wants to send some message M to a neighbor U, V is going to choose one of the random keys that we broadcast, XOR it with the message, and send it over the edge. Then in order to retrieve the original message M, you can XOR what it received with the same random key and get the message that V sent. And our goal is going to be to minimize the number of random keys that we need to broadcast securely. And we'll do this in steps. So our starting point is a simple solution where we simply broadcast a random key for every round of the algorithm and every edge. So in total, we broadcast n squared times r many keys. Then in each round, V, in order to send the message M to a neighbor U, encrypts the message using the corresponding key. And I would like to note that this message that V sends might be empty. As for security, because we encrypt each message using a unique random key, we get that this algorithm is secure actually with probability 1. However, this is quite expensive because we need to broadcast approximately n squared times r many keys. Okay, so the first step we do in order to reduce the number of keys is that we recall that the number of adversarial edges is at most f. And we are also going to use the fact that the algorithm is going to be secure as long as we use different keys to encrypt messages sent over these F adversarial edges. So what we can do is we are going to broadcast F square log n many random keys per round. So we broadcast approximately F squared times R keys in total. Then in every round, V is going to pick some random key from this F square log n collection and use it in order to encrypt the corresponding message that it wants to send. As for security, from the birthday paradox, we get that with high probability, indeed, we use different keys to encrypt messages sent over the F adversarial edges, and therefore the algorithm is secure with high probability. Okay, next, in order to improve the quadratic dependency on F, in the next step, we actually broadcast only F log n random keys per round. So we broadcast approximately F times R keys in total. Then in each round, instead of picking a single random key, V is going to pick approximately log n random keys and use their XOR in order to encrypt the message. As for security, it holds that with high probability for each adversarial edge, we are going to use at least one unique key in this XOR in order to encrypt the message sent over this edge. So here again, we get that the security holds with high probability. Until now, what we did is we sent a set of keys per round, and we didn't use the congestion parameter of the original algorithm A. Now, I'd just like to note that even if the original algorithm had low congestion, meaning that the actual number of messages sent over each edge is small, the secure algorithm will need to send a message on every edge and in every round. And this is because if, say, we don't send a message on some edge in some round in the secure algorithm, this can already leak information to the adversary that this edge was silent in this round in the original algorithm. Okay, so we are going to distinguish between two types of messages that we need to encrypt. Empty messages, where we didn't really want to send anything to you in the original algorithm, and real messages. And we'll deal with each type in a different manner. Okay, so our algorithm starts with broadcasting a collection of CF log n many random keys in total, and this is done using the secure broadcast algorithm. Then in round I, where V wants to send a message M to enable U, if this is a real message, meaning it's not empty, first V is going to pad it with log n many zeros to indicate to you that this is indeed a real message. Then, similar to what we did before, V is going to sample log n many random keys from this pool of random keys that we broadcast and use their XOR in order to encrypt this message. On the other hand, if M is an empty message, meaning V didn't really want to send anything to you, it is going to simply send a random string over this edge. Then when you encrypt the message, he's going to also receive a random string. So with high probability, the decrypted message is not going to start with log n many zeros, and this will indicate to you that this is an empty message and he can ignore it. As for security, first we show that both the encryption of empty and real messages are distributed uniformly, and therefore the adversary will not be able to distinguish between these two types of messages. Then we also show that with high probability, each real message sent over one of the F adversarial edges is encrypted using at least one unique random key, Ki in the XOR. And therefore, we show that the security guarantee holds with high probability. Okay, so I'll next turn to describe the secure algorithm for computing a minimum spanning tree. Now recall that in the minimum spanning tree problem, we are given a weight function defined on the edges of the graph, and the goal is to construct a spanning tree of total minimum weight. And obtaining security for this problem means that the eavesdropper is required to gain no information on the weights of the edges. Okay, so I'd just like to first note that any MST algorithm, even in the non-secure setting, have edge congestion that is at least square root n. Therefore, if we apply our compiler just as a black box on some non-secure MST algorithm, we will have a round complexity that is at least n to the power of 3 over 4, even for a constant number of adversarial edges. And this is too much for us, and therefore we are going to construct the secure algorithm in a more white box manner. Okay, so similar to many of the distributed minimum spanning tree algorithms, our algorithm is also based on the classical Barufka algorithm, which in the high level grows a forest of components using log n many iterations, where in each iteration we select an outgoing edge with minimum weight for each component and add these edges to the forest while ignoring cycles. Then our secure MST algorithm is going to contain two main phases. In the first phase, what we do is we apply a variant of Barufka's algorithm for log n many iterations, and we do it securely using our congestion-sensitive compiler. And this results in a forest of what we call basic trees, such that on the one hand, the diameter of each tree is bounded by square root n log n, and therefore we can perform aggregation inside these trees quite efficiently. And on the other hand, each tree is sufficiently large. It contains at least square root n many vertices. And we'll see shortly why these two properties are good for us. Then in the second phase, we start with selecting an arbitrary leader with a node by G star. And we also sample a collection of approximately square root n many random vertices we call landmarks. Now, because the size of each basic tree that we computed in the previous phase is at least square root n, we get that with high probability, each one of these basic trees is going to contain at least one sampled landmark. As for security, because these vertices that we choose are chosen arbitrarily, their identity does not leak any information to the adversary, and we can just choose them in an unsecure manner. Then the phase proceeds in log and many iteration, where we grow components that are contained in the minimum spanning tree. Okay, so we start with the basic trees that were computed in the previous phase, and we also keep the invariant that every vertex is going to always know which of its neighbors are included in the same component in this iteration. Then in each iteration I, first every landmark is going to compute the minimum weighted outgoing edge of its component that touches the basic tree Tj. And this can be done using simple aggregation inside the basic tree. And recall that these basic trees have diameter at most square root log n, so this can be done quite efficiently. And because that aggregation has congestion constant, so we can apply our congestion sensitive compiler and do this in a secure manner. Then in each landmark is going to update the leader G star with the minimum weighted outgoing edge that it shows, and this can be done using the secure unicast algorithm of Jane. Now, using this information, G star can locally compute the minimum weight outgoing edge of each component, and it also constructs the merges component for the next iteration. So it constructs the component of Si plus 1, and this can be done locally by the leader. Now G star is going to update each landmark with the selected edges and the new components. And this is again done using the secure unicast algorithm of Jane. Now each landmark is going to update the vertices inside the corresponding basic tree with the new edges and the new components, and this can be done using a simple aggregation inside the basic trees compiled with our congestion sensitive compiler. Okay, so this was a high-level idea of our secure minimum spanning tree algorithm. So to sum things up, in this work we provide F-secure algorithm for a collection of network optimization tasks, such as the minimum spanning tree, with round complexity that is at least for a small f that is polylogarithmic, nearly matches the existential bounds of the non-secure algorithms. Additionally, we provide a general compiler that transforms any non-secure algorithm into a secure round with round overhead that depends on the edge congestion. Okay, so I'll stop here and thank you for listening.